Hello! In this video we will be talking about resonance. We have started looking at the solution of the spring with a forcing term, and we have said that there will be some problems if some denominator would go to zero. We're going to be looking a bit more in depth about that. From now on, will be using handwritten slides. I hope this is not a problem. The reason why I chose to change is that honestly making fully typed slides was becoming a huge time sink. So I hope this is not a problem. If you have problems with my handwriting at any point, please come to me. I am doing the best I can. So let's go back to review what we saw in the last video. We were looking at the spring with the forcing term, and by applying the Laplace transform on both sides, we transform our problem from a differential equation to an algebraic problem that we can solve very easily. And then, with the inverse Laplace transform, we can find a particular solution. This is a general idea behind why we study Laplace transform in this course. But when we were looking at that, we found that the particular solution was a fraction with omega squared minus capital omega squared. And that might be problematic when small omega squared becomes very close to capital omega squared. The amplitude of our partial solution becomes very big. It's actually a danger when the natural frequency is close to the frequency of the forcing term. So when you're building something, you always have to think that the natural frequency embedded in your spring, that is the little omega, that was a ratio, like it was the square root of the ratio between k and the mass. You can, when you're constructing the spring itself, you can work on changing this little omega. And you want to be sure that that little omega is as far as possible from any forcing term frequency that you might be dealing with. Otherwise, you might have major amplitude, major oscillations and great amplitudes in them.